Okay. Buraya kadar sorusu olan var mı arkadaşlar? Okay. Alright, so we may start then section 26, so-called compact spaces. Those who have already taken Math420 have actually a strong background in compact spaces, probably. So here we will consider a general form of it, but most of the time it will be almost identical to the compactness concept covered in metric spaces. Okay, so let me start with definitions. First definition of an open cover. Okay, a collection A of subsets of a space X is said to cover X or to be a covering of X if its union if the union of its elements is equal to X. Okay, it is also called an open covering of X if its elements are open subsets of X. So, what's an open cover? It's a collection of subsets so that when you take the union of the elements in this collection, it gives us the whole space. Okay, if this is the case, then we call this collection an a covering of X. And if each A it's a subset of X, and if these are open, then we call this covering an open covering. Okay. Here is a definition, another definition of compact space. A space X is called compact if every open covering A of X contains a finite subcollection that also covers X. Okay. Sorry. Okay, let's see some examples and maybe non-examples. So real line with standard topology is not compact. Why is that? Well, it is because of the following. I can write R as the union of this collection of open sets and from 1 to infinity. So my an is just the interval minus 1 minus n, and my collection is this an's, okay? And they clearly cover R, but finitely many of them won't cover R, because when you have finitely many of them, their union is just another interval like this, right? These intervals are nested like this, minus 1, 1, minus 2, 2, minus 3, 3, and so on. So if you have just finitely many of them, a and 1, a and k, this is equal to what? This is just the largest one, right? Where n0 is the maximum of n1 up to nk. Therefore, any finite union of this open sets won't cover R. So I have an open cover, and this open cover has no subcover. Has no subcover. Therefore, R is not compact. Okay, since the open cover A has no finite subcover, R with its standard topology is not compact. Okay. All right. Another example. Well, this one is compact. This is as a subspace of is compact as a subspace of R standard. So what is this space? It is the following. I have 0 in the space. I have 1, and then I have 1 over 2. I have 1 over 3, and so on. I have 1 over n somewhere here. So I have only this, elements. So these are just elements of the sequence 1 over n together with their limit point, actually, which is 0. And we claim that this is compact. How can we prove this? Well, we have to apply the definition. So let uh, A be an open cover for X. Okay. Well, so X is just the union of this A alphas. Okay. Well, one of them should cover 0, should contain 0. Let alpha 0. Okay. is so that 0 is in this alpha 0, A alpha 0, right? One of them contains 0. Well, A alpha 0 is an open subset of this, right? Since A alpha 0 is an open subset of the subspace X, A alpha 0 is equal to what? It's equal to some open set, let's say U intersection X, where U is open in our standard. But you see, U is an open set containing A alpha 0, and therefore it contains 0 because 0 is here. Since 0 is in U, there is some R positive, so that 0, sorry, minus R, so 0 minus R, 0 plus R is also contained in U. Okay. Değil mi? Yani sıfırı içeren bir open setiniz varsa open set'in içinde böyle bir interval'ı da içeren, pardon, open set böyle bir interval'ı da içerir. Peki choose n0 so that n0 is larger than 1 over r. Okay. I can do this because the set of integers is unbounded and this is a positive real number. Therefore, there is always an integer larger than 1 over r. But then if n larger than n0, we have what? 1 over n, which is a positive number, of course, is less than 1 over n0, and 1 over n0 is less than r, right? I take r to this side and n0 to this side, so I get this. This means that 1 over n is in this interval, minus r, r, and of course 1 over n is in also x. So this means that it's inside A alpha 0. Okay, so that's inside in A alpha 0. So we have obtained the following. Hence 1 over n is in A alpha 0 for all n greater than n0. Okay, it means the following. Here I had 0, and this A alpha 0 is a set so that it contains an interval like this, R, R, and A alpha 0 is something slightly bigger than this, so A alpha 0. Of course, A alpha 0 is the intersection of this, something like this with x, and what we know is that all the terms of the sequence are here. So 1 over n, okay, 1 over n is inside A alpha 0 if n greater than n0. So what we see is then almost all the points of x are already in one of the A alphas. What about the rest? Well, there are only finitely many elements outside. I have one. Probably I have 1 over 2. Maybe I have 1 over 3 and so on. I have probably 1 over an minus, 1 over n0 minus 1 outside. The others are all inside a alpha 0. All right. What I will do, well, my space X is contained in this union. So every element of this containing 1, I mean including 1, 1 over 2, 1 over n0 minus 1, they are all in X. Therefore, each of them are in some A alpha. Okay, so I just pick those A alphas. Now for any K from 1 up to n0 minus 1, choose some alpha K so that 1 over K is in A alpha K. Well, then I have what? X, which was 0, and then union 1, 1 over 2. I have 1 over n0 minus 1, 1 over n0, 1 over n0 plus 1, and so on. Okay. 0, this element, this one, and the rest, they are in A alpha 0, and the other ones, only finitely many are left. These are in A alpha 1 and in A alpha n0 minus 1, right? So I have n0 minus 1, another one here. So n0 many A alphas covering X. So X is covered by finitely many alphas. Hence, in particular, X is covered by finitely many A alphas. Hence, X is compact. Okay? Because I just took an arbitrary open cover and showed that I can pick finitely many elements of that open cover that covers X. Okay? Sorusu olan var mı? Bu ikinci example'dı galiba, değil mi? Examples 1 dedik. Şuna 2 diyeyim şöyle. Okay. Üç. Şu interval'da yine subspace olarak is not compact as a subspace of R standard. Why is that? Well, this time let an to be this open sets. Yok. Böyle değil. 1 over n1. Yes. And from 1 to and so on. Şimdi her bir sıfırdan büyük sayı alırsanız whenever you take any point larger than 0, so an element of X, there will be some 1 over n which is less than X because the limit of 1 over n is 0. So this means that this X lies in this an. Therefore, the union of an's cover all X. So clearly X is the union of an's, so that A is an open cover for X. However, finite many of these won't cover A, right? If you choose 10 of them or 100 of them, they won't cover the whole interval because, you know, they will come up to some point, but after that they won't go further. So on the other hand, any finite union, let's say A and 1 union A and 2 union A and K. This is equal to what? This is just A and 0, so it is just this one, 1 over n 0, 1, where what is n 0? N 0 is the maximum of n1, n2, and k. And of course, this thing is not equal to 0, 1, right? And thus, any finite union cannot cover X. Thus, the space, okay, thus A has no finite subcover for X. Hence, X is not compact. Okay. Okay. We have, as usual, relative versions of these definitions. So suppose we have a space and a subspace. Then how can you relate compactness of that subspace to the compactness of the ambient space? So we will see that. First fact is the following. Let Y be a subspace of X. Okay. Then Y is compact if and only if every open covering of Y by sets open in X contains a finite subcollection covering Y. Yani bu diyor ki Y'deki open setlerle çalışmanıza gerek yok diyor. X'in open setleriyle çalışsanız da yeterli olur. Yani Y'nin kompakt olduğunu göstermek için şunu yapmak yeterli. Y'yi örten X'in açık kümelerinin herhangi bir collection'ını alacaksınız. O collection'ın sonlu bir alt collection'ını bulabiliyorsanız her seferinde yine Y'yi örten, o zaman o şey olacak. compact olacak. Yani y'nin open setleriyle uğraşmanıza gerek yok diyor. Nedeni de bariz tabi. Neden? Önce şu yön yapalım. So assume Y is a compact space. So as a subspace, I assume that it is compact. What I have to show is the following. If I have an open covering of Y by the open sets in X, then that collection has a finite sub covering of Y. Okay. Let A ya da şöyle diyeyim, O diyeyim, O alpha be an open cover. Okay. Be a collection of open subsets of X so that Y is contained in this union. Y doesn't have to be equal to this one. Okay, probably this union is much bigger. For example, take Y to be this gadget, 0, 1 over 1, 1 over 2, 1 over 3, and so on. And open sets, are intervals like this, elements of O alpha. Of course, each of these has uncountably many elements. So they are much bigger than this gadget. Okay. Now what I have to show is the following. Finitely many of such O alphas covers also Y. How can we show this? Well, then, of course, let A alpha to be just Y intersection O alpha, which are open subsets of Y, because they are open subsets of, they are the intersection of Y with open subsets of X. Therefore, they are open in Y. But then, okay, since okay, I have this. And of course, this is inside this. I can take intersection here. And this is equal to what? This is equal to union of O alphas intersection Y. But these are just A alphas. And A alphas, of course, are subsets of Y. Therefore, this is contained in Y. And this implies Y is equal to this union. But since Y is compact, finitely many of such A alphas cover A. We have Y is equal to A alpha 1 union A alpha K for some alpha 1 alpha K in the index set, and K being a positive integer. But if this is the case, then of course Y, so what is A alpha? A alpha is just Y intersection O alpha 1 union Y intersection O alpha K. But what is this? This is just Y intersection of the union, and this implies Y is contained in O alpha 1 union O alpha K. So what we did, I started with an open collection of open sets covering Y, and I showed that Y is contained in finitely many of them. So this proves, this finishes the proof of the this part. For the converse, you have to, just reverse this argument. I will leave it to you, okay? The other direction is left as an exercise. Kitapta da sanırım vardır bu. İspat var, evet. Yani benimkinden daha da kolay, muhtemelen daha da özetlemiş. Oraya da bakabilirsiniz. Peki. Sorusu olan var mı? Any questions so far? Alright, here is another theorem. Every closed subspace of a compact space is compact. Every closed subspace of a compact space is compact. So if the bigger space is compact, then maybe not all subsets are compact, but the ones which are closed are necessarily compact. Proof is very easy. Okay, so let Y be a subspace of a compact space X. I want to show that Y is what? Y is compact. So take, I'll do the I'll use the result we just proved. Okay, characterization of compactness for a subspace. So let O alpha be a collection of open subsets of X covering Y. Yani elimde şu var. Y şunların içinde. Okay. Böyle bir covering'imiz var. Benim ne göstermem lazım? Bunlardan sonlu tanesi Y'yi örter. Must show Y is contained in the union of finitely many O alphas. Well, let's see why this is the case. Well, it is the case because of the following. Note that if I add one more open set to this collection, then I will cover the whole space X. Okay, X is equal to what? This is equal to Y union X minus Y, right? And Y is contained in this union. And I have this union and one more subset which is also open, where X minus Y is also open because Y is closed. Okay, well, then this thing is of course this thing is equal to this is equal, this is inside X, where hence X is equal to this collection, union of this collection, I mean union of the elements of this collection. Okay, all elements are, all subsets are open. These are open. This is open. Since X is compact, we have finitely many elements of this collection should cover X. So I have O alpha 1, O alpha k, and possibly X minus Y. Okay, for some alpha 1 up to alpha k. Okay, well, then of course Y, which is just Y intersection X, therefore this is just O alpha 1 union O alpha k union X minus Y. So I have this. Okay, so let me write it this way. So this implies Y is what? Okay, Y intersection O alpha 1 union Y intersection O alpha k union Y intersection X minus Y. Well, this is just the empty set. Therefore, Y is equal to this union. Sorry. But this means what? Y is contained in O alpha 1, O alpha k. And this is what we wanted to show, right? Y is contained in the union of finitely many O alphas. That's exactly what we have achieved, so that Y is compact. All right. You may wonder why the whether the converse statement is true or not. The converse statement is not true. In other words, if you have a space, a compact subspace may not be closed. However, it will be closed if we assume that our space is Hausdorff. So that's a phenomenon that doesn't occur in metric spaces because they are all Hausdorff. But when you go outside, that comfort zone, so if your space is not Hausdorff anymore, then weird things may happen, and this is one of them. A compact subspace may not be closed anymore, but so in case of Hausdorff spaces, life is easy. I will show also an example where you drop the Hausdorff assumption and you end up with a compact subspace which is not a closed subspace. Okay, every compact subspace of a Hausdorff space is closed. Okay. Ne kadar zamanım kaldı? 10 dakikam daha var. Okay, so let Y be a compact subspace. Subspace of a Hausdorff space X. Okay. I need to show that Y is closed. We will show the following. Must show X minus Y is open. Okay. Well, how can we show this? Take any point x0 in x minus y. Okay. Now, for any y in y, x0 and y are different points, right? Because x0 is in x minus y and y is in y, so we have this. Well, I have 2 points which are distinct and I am in a Hausdorff space. So there are, okay, since x is, okay, x is Hausdorff, there are open sets. There are open subsets. Okay, u, y, and vy, so that uh, x0 is in uy and y is in vy and uy intersection vy is empty. Okay. Well, for each y, I have such a y. Since y is the union of 1-point sets, right? And each singleton is contained inside vy. We see that the collection of open subsets of X, which collection? This collection. Vy's, Y in Y, okay, is an is a covers Y. But we know that Y is a compact subspace. Therefore, finitely many of these covers Y. Since Y is compact, Y is contained in, let's say, Vy1, Vy2, Vyk for some Y1 up to Yk in Y. So finitely many of them should also cover Yk. Okay, now let V to be union of these, and U to be the intersection of these gadgets. Okay. Okay. Ne yaptık şimdi? Şunu yaptık değil mi? Ee, bir tane x noktası seçtik. Pardon. X0 seçtik. Y'nin dışından. Sonra Y'deki her nokta için şimdi burada open setlerim var. Şurada da bizim Y subsetimiz var. Y'ı içine alan open setler buldum. Right, these are VYIs. And here I have UYIs. And so on. Okay. Finitely many of them. Now, this UIs are open sets and their intersection is an open subset, right? Then U is an open subset containing x0 and moreover U intersection V is what? V is the union of this red open sets and U is the intersection of blue ones. This thing is equal to what? U is the union of, no, intersections of U i's. V is the union of VJ's. They're all finitely many. From both of them are from 1 to k. And this thing is what? This thing is just nedir bu? Union of the intersections. U, Y, I intersection VJ'ler. I o intersection yok. Şöyle yapabilirim. Pardon. Şunu şöyle yapayım. Daha dikkatli olmam. This is the intersection from 1 to k of y I with the union of VJ's. O da doğruydu da sanki amacına yani o da doğru. Şimdi bu nedir? Yani şu kümenin şeyle ara kesisine bakıyorum. Şöyle diyebilirim. Bakın bu şunun içinde. Bu bir dakika. Şimdi bu şunun içinde union C üzerinde union alıyorum ve intersection of UI'ların VC ile intersection'ına bakıyorum. Şöyle yazayım. Tamam. Bu şunu içeriyor tabii. Evet. Bu intersection'da ne var? Şurası şeyin içinde. Şimdi intersection of U, Y, I's intersection VJ bu şunun içinde kalacak. U, Y, J intersection VJ V, YJ. But this intersection is empty. Okay? Therefore, this intersection is empty. So what we see is then, hence, x0 is in this open set. And this lies outside of the union of V, Y, I's, but that's inside x minus y. Yani bu mavilerin ara kesiti kırmızıların union'unun dışında. Dolayısıyla da kırmızıların cover ettiği y'nin de dışında. O halde ne buldum? Bu open set x0'ın etrafında ve y'nin dışında kalıyor. Dolayısıyla da x minus y so that x minus y is open. Okay, this finishes the proof. This means y is closed. So this finishes the proof. Okay, I took 6 minutes of your break time